Propane is an important commodity in Canada whose many uses contribute to our high quality of life. Uses that include heating our homes and playing an essential role in many industrial applications. The safe transportation of propane is a top priority for government and industry. Propane transportation is done in strict adherence to standards for means of containment, training of personnel, and other rules as prescribed in the Transportation of Dangerous Goods Act and regulations. There are literally thousands of shipments made daily in Canada with an excellent safety record.
This video and the research it describes were developed for the research group in the Transport of Dangerous Goods Directorate. We are a branch of Transport Canada that investigates and researches technical and other questions surrounding the transport and regulation of dangerous goods. This research was also conducted in cooperation with the Liquefied Petroleum Gas Emergency Response Corporation, a leading industry emergency response organization. While accidents involving propane are very rare events indeed, it is important to be prepared. There are well-established techniques for dealing with propane emergencies, and new techniques are always being explored in an effort to further improve safety. It is in that vein that we present this video, The Last Resort, Vent and Burn.
What typically happens in the event of an emergency involving a damaged LPG tank is the emergency response team assesses the situation and decides, with the help of experts, whether one or more of several well-established techniques can be applied to render the situation safe.
It is important to remember that it is standard practice for the first response community to call upon industry response personnel in the event of an accident involving propane. These industry responders play a major role in assessing the incident and in determining the best way to deal with the tank and its contents.
There are many factors to consider when assessing an accident situation involving a propane tank truck. A few of the more important questions to answer include: is there a leak? And if so, what is the risk of ignition and potential consequences to people, property, and the environment? Is there appropriate personal protective equipment, and are detectors available? What is the status of the valves and fittings? Are they accessible and functional? What is the extent of tank damage? Does an examination of the surface of the tank reveal cracks, scores, gouges, or dents, particularly at weld zones? Is the tank damage severe enough to pose an imminent risk of catastrophic failure? First responders and industry responders apply their knowledge and experience, and working as an effective team, bring the situation to a successful conclusion. The purpose of this video is to add to the knowledge base of the first response community by presenting the results of research conducted by Transport Canada and the Liquefied Petroleum Gas Emergency Response Corporation into the approach we call Vent and Burn. It is intended to orient the viewer should he or she be faced with a situation where use of a well-established technique, such as product transfer or flaring, is not feasible, and undertaking a vent and burn is clearly the only option left. Please note that the experimental results shown in this video were obtained under ideal circumstances. The experiment used an undamaged tank with functioning valve systems. The tank was positioned ideally for the experiment, under ideal weather conditions and so forth. In other words, none of the complicating factors typically requiring assessment at an accident scene had to be considered, and the results shown in this video would not necessarily be reproduced in the field. So what are we talking about when we speak of a vent and burn? It is basically a controlled technique which involves using small, shaped explosive charges to blow small holes in the top of a highway propane tank truck with simultaneous ignition of escaping pressurized gas. This controlled burn at the top of the tank quickly lowers the pressure inside the tank, thereby reducing the likelihood of catastrophic failure. Shortly after, once the pressure in the tank has been relieved, similar charges are used to blow holes in the bottom of the tank, allowing the LPG to escape rapidly and burn off into a drainage area for controlled burn. Let's look more closely now at the experiment and review the considerations that were necessary to ensure a successful test. All of these steps would need to be followed in a real accident situation where a vent and burn was being considered. First, we conducted the experiment in an extremely remote location to eliminate potential hazards to surrounding communities. This also allowed the observation team to observe at a safe distance. High-speed cameras operated remotely were used to collect images and compile this video. We ensured that the tank was safe from accidental ignition while preparing for our test. All precautions were taken to keep the tank from moving during our preparatory work and, of course, during the experiment itself, and particularly after being subjected to shock from the explosives. The area around the base of the tank was dug out to provide a basin to accept a fast flow of burning liquid. We measured wind speed and direction in order to calculate the potential fire exposure zone and the dispersion of the smoke cloud. Only highly qualified experts in tank car engineering and in the use of explosives were competent to undertake key tasks in this experiment.
We must stress that this video shows an experiment conducted under highly controlled conditions. Use of an approach, such as this in the field, would have to be considered very carefully. What follows is a description of the actions that we took during the actual experiment. Personnel donned appropriate safety equipment, and appropriate detectors were used to ensure that there was no hazardous atmosphere present.
A close inspection of the surface of the tank followed to ensure that there was no apparent damage and the valves were not leaking.
We conducted an assessment of where the burn reservoir would likely form.
It was decided to dig a shallow 45-degree fan-shaped reservoir area where the liquid propane would be collected as it left the bottom of the tank. We knew that the maximum burn-off distance was about 20 to 30 meters from our tank. We wanted to be sure that the liquid propane would stream away from the tank rather than pool around and burn the tank itself. A tank expert had determined the thickness of tank shell and provided this data to the explosives expert, who then used his expertise and experience to determine the number and size of the shaped charge explosives that were used.
And that way, if we get, even if it flashes back from all the way back there, which
it's only
it shouldn't, but it's a backup, right?
It's only going to take one to do it.
According to Transport Canada, highway tank walls range in thickness from 7.1 millimeters to 16 millimeters. Specific tank thicknesses can be obtained from the specification plate on the tank or the manufacturer. After placing the charges, the explosives expert ran separate lengths of detonation cord to the top and bottom ends of the tank and connected to each charge. All charges in the same location were designed to go off at exactly the same time. Since two separate circuits were used, we were able to detonate each set of charges independently. The explosives expert set up the spark ignition sources around the detonation sites. Our experimental procedure used off-the-shelf shaped charges. We placed 3 charges on top and 4 were placed on the bottom. The number of holes determined how fast the tank pressure reduced. In our tests, the bottom holes were punched while there remained a relatively high internal pressure. The optimal bottom detonation is when the internal pressure is at near atmospheric. The signs indicating near atmospheric pressure included a frost line that appeared on the side of the tank and the greatly decreased height, intensity, and velocity of the burning flare. Our experiments have shown that there is a risk of fracturing the tank when the bottom charges detonate on a depressurized refrigerated tank. Reducing the pressure lets the liquid propane leave the bottom of the tank in a controlled manner for burn-off. With the tank pressure relieved, there are no pressure-related hazards, such as rupture with associated projectiles. The small magnetic charges punch holes into the tank, allowing gas to vent. Our explosives expert placed the charges at 2 locations, at the top upslope end of the tank and at the bottom downslope end. Each set of shaped explosive charges was on a separate circuit, so that there was no danger that both could be detonated at the same time. Both detonation sites included devices to ignite propane flow. For greater safety, we placed backup ignition stations around each vent location, as failing to ignite at the appropriate time would have generated large volumes of gas or liquid that, if ignited, could be extremely hazardous. Once started, the entire quantity of propane was burned in 38 minutes. These first Canadian tests of vent and burn were very encouraging.
Our understanding of this technique has been greatly advanced by the research described in this video. It is true that vent and burns have been used in prior accidents as a last resort. In most cases involving rail cars, this technique greatly reduced the time frame in which people and property were at risk. However, more research and experience is required before most emergency responders will feel confident in knowing whether it is feasible or appropriate to use vent and burn when managing a real accident. As a consequence, Transport Canada will continue to assess whether the vent and burn technique can be an effective last resort in responding to LPG events.
For more information, please contact the Research, Evaluation and Systems Branch, Transport of Dangerous Goods, Transport Canada.